This is video 7 of Unit 12. In this video, we'll do a few more calculations based on the heating curve. Now, these calculations will be a little more involved. They'll involve more than one step. So let's see if we can take them to task. So here we say, number 7 says, how much heat does it take to raise 36 grams of ice from negative 15 to 55 degrees Celsius? Now, if we take a look at the heating curve, what we're talking about, there are 5 portions to the heating curve. We are talking about melting, we're talking about going from negative 15 ice to 55 Celsius water. We're actually going to go through 3 portions of the curve. In fact, we are beginning below the melting point of ice. This would be 0, this would be 100. So we're actually beginning somewhere right here. We have to heat up the ice, then we have to melt the ice, then we have to heat up the water to about 55 degrees Celsius. So this will involve 3 different problems. We're going to heat up the ice, we'll call that A. We're going to melt the ice, we'll call that B. And we will heat up the liquid, we'll call that C. So we actually have 3 separate equations, and then we'll have to put them all together. So equation A will involve heating up the ice. Now remember, if it's a diagonal portion, we're going to use the equation with 3 parts. So we're using the equation that says heat equals mass times specific heat times change in temperature, the famous MCAT equation. In this case then, let's go ahead and put the mass. Our mass is 36 grams. C, specific heat of ice, is actually given to us here as 2.05 joules per gram degree Celsius, so 2.05. And change in temperature, now, it's going to be just this portion right here. So from negative 15 to 15, that's only 15 degrees Celsius. So this, we're going from negative 15 up to 0 degrees Celsius. So from negative 15 to 0 is what we've got there. Okay, so if we calculate this out, go ahead and do this on your calculator. We have 36 multiplied by 2.05 multiplied by 15. This gives us 1,107. Now, I'll go ahead and keep significant figures until the very end. The more important thing here is to realize that this is joules, not kilojoules, this is joules. So this is our first mini answer. Now for part B, what we're doing is we are going to melt that ice. Now to melt the ice, we're going to have to use the equation with 2 parts, which says heat is moles times heat of vaporization. In this case, we're melting, so we'll call it heat of fusion. In this case, we have to do moles. Now moles, we have to convert from grams, so we have to do a little separate conversion. So let's do that up here, and we have 36 grams of water. And as we convert from grams to moles, remember this is water, and this will be easy because it's always going to be the same molar mass. So grams go down here, 1 mole goes above, and it's 18.02 grams for 1 mole of water if you look at the periodic table. So this actually gives you exactly 2.00 moles. So our moles is 2.00. Which means we can now have 2.00 moles multiplied by heat of fusion of ice is given as 6.03. So 6.03 kilojoules per mole. And effectively we're just multiplying that by 2, and that gives us an answer of 12.06 kilojoules. This is our second mini answer. And the third mini answer, part C, will be we're heating up the water now. We've melted all the ice, now we're heating up the water. In this case, we're going to have to use the equation with 3 parts again because it's the diagonal portion. So we've got the MCAT equation again, and this gives us, do it down here, this gives us mass again as 36 grams. Now the specific heat of water, you don't use the specific heat of ice anymore, you'd have to use that of water. In the previous slide, we saw that the specific heat of water was 4.18 joules per gram degree Celsius. So that's the number we'll use, 4.18 joules per gram degree Celsius. Our change in temperature now. We're going from 0 Celsius, that's where we melted ice, up to 55. So this will actually be 55 degrees Celsius. Again, this is 55 minus 0. That's how we got that number. Okay, go ahead and plug this in. And we got 36 times 4.18 times 55. This gives us 8,276. In this case, it'll be joules. This is our third mini answer. Now, we've done the 3 parts. The last thing to do is to put them all together. What I'll do is I would recommend putting all 3 in the same unit. You can't really add them up without putting them in the same unit. So why don't we put all 3 of them, usually you put them in kilojoules. In order to put this into kilojoules, you would divide by 1,000. You always divide by 1,000 because if you took a look at the setup, you've got 8,276 joules. You have to put joules down here, and you have to put kilojoules up here. 1 kilo is 1,000 of that joules, if you were going from kilograms to grams, for example. So it's always divided by 1,000, which means this number right here is 8.276 joules. And this number right here is 1.107 kilojoules. Oh, kilojoules. Sorry, not joules, kilojoules. There we go. And now we can add the 3 numbers together. So let me cross everything out. That's like a medium step. So let's go ahead and add these up. So I'll add the 1.107 plus the 8.276 plus the 12.06 for a total of 13. Carry the 1. We got 14. Carry the 1. We got 4. And here we have 11. Carry the 1. 21.443. Now let's take a look at the significant figures. We have 2 significant figures, so really 21 kilojoules is our final answer. 21 kilojoules. Here's our final answer. So if you want to take ice that's pretty cold at negative degrees Celsius and warm it up to warm water that's at 55 degrees Celsius, you have to put in 21 kilojoules of heat, and that's the idea. This is pretty involved, pretty messy. To reward your patience, let's do one more. And this one actually, let's see, very similar, but it says how much heat will be released to the outside when 3.5 moles of steam at 100 degrees Celsius condenses and cools to 25 degrees Celsius. What we're doing here is we're going backwards. By backwards, I mean we have our heating curve with the 3 parts. We're beginning with steam at 100 degrees Celsius, condenses and cools to 25 degrees Celsius. So here we have steam at 100 Celsius, and for water, this is 100 Celsius. And we want to get it down to regular water at 25 degrees Celsius. So we want to come down here. We have to go through 2 portions of the heating curve. We have to we have to condense the steam, and then we have to cool the water. So we have, let's say this is A and this is B. So part A will require us to use the 2-part equation. Heat is moles times heat of vaporization in this case. Now it doesn't matter if you're boiling or if you're cooling, the same equations apply. And that's the idea here. So our moles in this case are 3.5 moles. Our heat of vaporization again is given as 4079 kilojoules per mole. So what we'll do is we will multiply these 2 numbers. So go ahead and do this in your calculator. 3.5 times 40.79. This should give us 142.76, or 7, we'll say 0.8 in this case. And this is kilojoules. So as we're condensing the water, that much heat is released. And then let's do part B. In this case, we want to cool the water down to 25 degrees Celsius. So we're going to have to use the equation with 3 parts because this is a diagonal portion. So the equation says heat equals m cat, which means we have ourselves the mass. Now the mass we'll have to convert again from grams to moles, but in this case backwards, from moles to grams. So 3.5 moles. A mole of water, it's always going to be water, is 18.02 grams of water. So if you multiply 3.5 times 18.02, should get yourself 63.07 grams of water. And that's what would go for our mass. So 63.07 grams multiplied by the specific heat, again, is given here as 4.18 joules per gram degree Celsius, and our change in temperature. Now we're going to go from 100 down to 25, and we're only going through one portion of it. So this would be 75 degrees Celsius. So if you want to say 100 minus 25, that's how we got that number. Go ahead and multiply those numbers. 63.07 multiplied by 4.18 multiplied by 75 should give us 19,772. Now this would be joules again because we're, remember, anytime we're on the diagonal portion, we're going to use joules. On the flat portions, we'll use kilojoules because it takes more heat to undergo a phase change. This will be joules. All right, now we have to add the two numbers together, but let's first put this into kilojoules. So we'll divide by 1,000, and that simply gives us 19.772 kilojoules. So now we're going to actually use this number. Add the two numbers together. Go ahead and add them up. And the total number, we'll put all the way down there, would be, you can do this in calculator if you like, should be 162. Now we have two significant figures, so 160 kilojoules. Now this is quite a bit of heat. Kilojoules is a lot of heat. So it will release 160 kilojoules of heat as you condense that water. Now this is mostly because condensing water produces an enormous amount of heat. This is why storms are actually very energetic, is because in the air, water is condensing, releasing all that heat. So hopefully this makes sense. Go ahead and do your own problem here, practice problem 7 and 8 together, and we will talk about this and have more practice in class. So this concludes for us the last video of chapter 12.